basically a sort of disturbance. So whenever we talk about waves, what comes to our mind is some sort of a actual wave, because the word wave refers to an ocean that we see that rises and fall. But in physics, wave has a very specific meaning. It means some sort of a disturbance. For example, when we talk about a wave, we are actually talking about if we have many trees here, all these trees, we have many trees here, and if someone disturbs them by pushing them somehow, pushing them in this direction, they move back and forth. So if they're like this, they move back and forth, this direction, then this direction, back and forth. This is a type of a disturbance. Or if someone takes a piece of rope or something, a piece of rope, and they just takes this end and they just jolts it somehow so that it moves and it is disturbed. So that disturbance could be shown off like that. So these type of disturbances are called waves. So the first basic idea of wave is that there's some type of disturbance, as a specific disturbance. Now the disturbance might flow, but not necessarily the object might flow. For example, when we see a wave going through on a field of tall grass, we will see that maybe the disturbance is caused by the wind. We will see that all the tall grasses, the trees, they're moving back and forth, and from a large bird eye view, it looks as if something is moving on through the field, some sort of a disturbance, but the actual trees are not moving. So it is the disturbance that is moving, but the actual objects are not moving. So the same thing can be seen in some sort of a sports where we have the wave of the audience. This is usually seen in many football tournaments where one audience member stands up, then he sits down, and the next one stands up and sits down, and this goes on throughout the gallery of the audience, and it looks as if a wave is passing. So it is some sort of a disturbance. The actual person is not moving. He's sitting in his seat. He's just standing up and sitting down. But it appears that there's a disturbance created, and the disturbance is moving throughout the stadium. So this concept is an important concept, that wave is a disturbance. Now the object might not be moving. So like in a field of grass field where the grasses are, the wind is making a wave flow through it, the grasses are actually not moving. So the wave can be a standing wave, where the object of the wave is not moving. It can be a standing wave. So standing wave refers to where the actual objects are not moving. But that does not mean that all waves are standing waves. There are waves where the actual object are also moving, apart from the disturbance. So both the disturbance and the object can be moving. An example of a wave where something is moving could be the word most associated with waves, water waves. Sometimes we can think of water wave where the actual water is not moving, because so we can have a situation where there is a boat on a little lake, and you can see that there is a wave, but the boat is not going anywhere, meaning the boat is going up and down. The boat is just going up and down. So we can think of this as a standing wave. So where the boat is in the water, and there is some sort of a movement in the water, but the boat is just moving up and down. So this type of a motion of the wave because of the disturbance, this is a standing wave. But on the other hand, both the boat can go up and down, and also the water, the wave of the water can also carry it forward as well. So the disturbance could actually carry the object. So this is not a standing wave, but it is a moving wave. So both type of waves can happen. But let's talk about the motion of the disturbance, whether it's a standing wave, whether the actual object are moving or not. Let's talk about the motion of the disturbance itself. Now think of someone sitting on a camel and traveling through camel. So if someone sits on a camel and travels through camel, this is let me try to draw the hump of the camel. This is what the hump of the camel looks like. Maybe this is the camel. So this is the camel. So if someone sits on a camel, so what would happen? The person would move up and move down, move up and move down. As the camel moves forward, the person is going to bounce up and down on the back of the camel. This type of disturbance of the wave, this type of disturbance is called a transverse wave. So a transverse wave is a type of disturbance where while the object is moving forward, the actual particle is also moving up and down. So it is moving perpendicular to the motion of the actual disturbance. So this type of movement of the wave, this type of disturbance is called a transverse wave. Now think of someone moving in a very fast motorcycle on a smooth road. In that case, what would happen? If someone travels on a very fast motorcycle, so what would happen? The person, because of the speed, would move back and forth. If the motorcycle is moving in that direction, the person might move back and forth because of the wind and the slowing of the speed of the motorcycle and so on. So the person would actually move back and forth. So it would move parallel to the motion of the actual motorcycle. So this type of disturbance is called longitudinal wave or longitudinal disturbance. Remember, we are actually talking about how the wave is moving. Wave means a disturbance is moving. So how the disturbance is moving. So we are talking about this. So when we describe something, we have to understand first of all, in this particular case, how it is moving. So if you're talking about a person, you might say how a person is standing in one place and dancing around. So there is two types of dancing, as transverse wave dancing and the longitudinal wave dancing. Transverse wave dancing means this motion is perpendicular to the actual motion of the object that is having the disturbance. And another thing can be a person is moving and dancing at the same time. So it's not a standing wave, the object is actually also moving. Now when we talk about anything, we have to talk about what it looks like. Now usually from the word wave, what actually puts in our head is some wave of ocean, and that's it. All the word wave, since it is taken from the word ocean wave or anything, we always think about ocean rising and falling, but that not necessarily is the case. A wave is any disturbance. Now but we can actually represent this disturbance on a piece of paper very interestingly. For example, you have a piece of paper. So suppose you have a piece of paper that's going to be, this is a piece of paper, and someone is going to pull the piece of paper in this direction. Someone is going to pull the piece of paper in this direction, and as you do this up and down motion, so what's going to happen? So you're going to move this in a perpendicular way. So the disturbance that you're going to do, just this. So there's, suppose this is a thing just moving up and down. It doesn't mean, it doesn't look like anything, but as you do this, if someone pulls this paper, it looks like this, because the person is actually pulling the paper. So this is what it looks like. So this is how we can represent a wave. Now when we say up and down, we are actually talking about transverse wave. As the object is moving, the disturbance is up and down. The same thing can be done using another piece of paper like this, and suppose someone is pulling in this direction. So this time it is going to move parallel to the motion. So if it moves parallel to the motion, back and forth, even that can be represented like that. It can be also look like this, no problem at all. So even it is longitudinal wave or transverse wave, it can be represented like this. This is actually how some heart machine shows the heartbeat. It is actually not beating like that, but if you have a pen who bounces at every beat of the heart and there is a paper that is being scrolled around, it can look like that. Now this thing looks like something in maths, and we can describe what we see. This is what is done for description. First of all, we have to remember this wave is going to go on forever and forever and forever and forever and forever and forever. It's going to move on forever. So what we do, the first thing we do is draw a line in the middle, some sort of an axis. We just draw a line in the middle, and from this is called the crest, the upper part. So from one crest to another crest, this is called the length of the wave, or the wavelength, used by the letter lambda. The wavelength is from the one crest to another crest, the distance actually. Wavelength can also be measured from trough to trough, trough to trough, like this. This is also wavelength. As a matter of fact, wavelength can be calculated in many ways. For example, some common ways of wavelength is, this is a wavelength, also referred to as the sin x mathematically. This is also a wavelength. This is minus sin x. Then this is a wavelength. This is referred to as cos x. This is also a wavelength. So these are all representatives of wavelengths. So whenever you think of a wavelength, it is actually the description as we describe it, what we see mathematically. This is a wavelength. Next thing that we have to understand is concept of time period. Time period is actually the time taken to cover one wavelength. So that's the time period. So T, or the time period, time taken to complete one wavelength or one cycle. We can call this wavelength a cycle. This is a cycle, this is a cycle, and so on. So that is T. Another thing that we have to understand is the frequency. Frequency, whenever we are talking about frequency, we are talking about 1 second. Frequency refers to as 1 second. So frequency refers to number of cycles, meaning wavelengths, in a second. So in 1 second, this is very, very important. 1 second, we are talking about how many wavelengths have been completed if something is traveling. But when we talk about time period, we're talking about 1 cycle, not 1 second. It is the amount of second that is needed to cover 1 cycle. That is extremely important. And there is a connection between the two, which is denoted by frequency is the reciprocal of time. Time is measured in second, so frequency should be measured in 1 by second. So it should be measured in 1 by second. But we use another term called hertz. So frequency is actually measured in hertz, which means 1 by second per second. Another formula that links everything, if a wave is disturbance is moving, whether it is standing wave or a moving wave, that speed of the disturbance is, we know speed is usually distance by time. We know from this, speed in one direction, because the waves move in one direction, can be called velocity, and distance is the total wavelength, how many wavelength that we have. So if we have a distance of one wavelength, and the time taken to travel one cycle or one wavelength is t, and we know 1 by t is f. From that we can get the important formula v equals to f lambda. Very important formula, v equals to f lambda by basic algebra. All these formula are not very complicated, they're just basic formula. So that is a very, very important feature. Now one thing that might be talked about, we have talked about how the waves travel. Now we need to talk about a very important type of wave. It's a type of wave, and that type of wave is called transverse wave. type of wave which travels like a transverse wave. It's called electromagnetic wave. This is now a type of wave. An electromagnetic wave travels by creating an electromagnetic disturbance. Suppose we have a particle here. That particle is an electric charge. This electric charge, this falls under electromagnetism, creates some sort of a disturbance like this. Because the charge, they create some sort of a disturbance. Now this disturbance creates another disturbance called the magnetic disturbance. So it is like this. Suppose one disturbance is in the x-axis like this, and the other disturbance is in the y-axis like this. They're perpendicular to each other. So this disturbance creates this disturbance creates this disturbance, and they keep on moving, and they can move through a vacuum. So this is some sort of an electromagnetic wave. An electromagnetic wave is a special wave. There's a particle called photon, and the photon, it has a charge, and that charge, electric charge, creates a magnetic disturbance, a magnetic field. The magnetic field disturbs an electric field perpendicular, and they travel in a very snake-like double snake. If we have two snakes, one perpendicular to the other, joining together, each disturbing the other, and they travel like this, like a double snake way, and that's a electromagnetic wave. How do they travel? They travel in a transverse wave disturbance because they're moving perpendicular to motion. You have to remember that. So this travels like this. Now there is another type of wave that's called sound waves. Sound waves needs to travel through a medium. Electromagnetic wave do not need any medium to travel. Sound waves need a medium to travel. So they need, for example, air and water or any solid. Sounds can also travel. They travel in the form of longitudinal disturbance. That's how they travel. They travel in a form of longitudinal disturbance. That's how they travel. So this is a type of wave. This is how they travel. This is a type of wave, and this is how they travel. Now while talking about this, one thing must be mentioned about frequency and wavelength. The longer the wavelength, the lower the frequency, because in 1 second you cannot just cover that wavelength. So if we talk about, if you see a description, this is 1 second. So 1 second it travels one wavelength that has a frequency of 1 Hertz. This, in the same time period, it travels 2 wavelengths. This is a frequency of 2, so f equals to 2 Hertz. This again in 1 second travels 3 wavelengths, so this is a wavelength of 3 Hertz. So the shorter the wavelength, the higher the frequency. So you can say that f is inversely proportional to wavelength, or wavelength is inversely proportional to f. That is how it works. So when we talk about the electromagnetic spectrum, we are actually talking about a number of things. First of all, the shortest wavelength. The shortest wavelength are gamma rays. These are the electromagnetic spectrum. This is the shortest wavelength. Longer than this, they are the X-rays. Longer than these, they are the ultraviolet rays. Okay, so this is on one side. Then in the middle there is light. So this is lower than light. Now higher than light, what we have, the largest is going to be radio waves. Smaller than the radio waves are the microwaves. They are 2 or 3 inches long. And longer than that and closest to the light boundary, they are the infrared rays. So we have 1, 2, 3, 4, 5, 6, 7. We have the spectrum, 7 electromagnetic waves. Magnetic waves. So we have this 7 electromagnetic waves. So whenever you're talking about that, you have to remember this is the electromagnetic spectrum, a type of wave. The most important wave to study is this type of wave, electromagnetic wave. Someone will say that it's only wave to study. Interestingly, light can also be divided into 7 parts, and the shortest wavelength is violet, so lower than violet is ultraviolet, and the largest wavelength of light is red, so larger than red is infrared. So that is how it is working.